Okay, so good morning, all of you. Before we start, I need to make a small announcement for today's session only that today I'm using a Windows-based system, so we might face some technical glitches in between. So kindly bear with me. Instead of the usual Ubuntu-based system, today I'm on a Windows laptop and I'm using this Webex app. So don't know if it will work fine or not. If it doesn't, then we will try to keep the lecture going, but if at all there is a case that we won't be able to conduct the lecture, then we will arrange a separate session later on. So today, let us start from the point where we left, and I think I shared this PDF file with all of you through the Google Class Drive, and we were on this point that if the signal is time limited, then it cannot be band limited, and if the signal is band limited, then it cannot be time limited. Okay, so this was TL and BL thing. A signal cannot be both time limited and band limited. Okay, but yes, it can be time unlimited and band unlimited. So we stopped at this point. Why we were studying this was that we studied the sampling theorem in an idealized setting. It means we thought that, let us say that the sampling theorem was studied. The sampling theorem was studied assuming that the continuous time signal exists for minus infinity to infinity. Hence, assuming that its spectrum is baseband or it's a low pass signal is a valid assumption. It means that this case can arise. That let me write it down. So, Simon Theorem was studied assuming that the continuous time signal exists for minus infinity. Hence, it is possible that it is a low pass signal, low pass or band limit. Okay, whatever it called. These two terminologies are quite similar in most settings, but in a few settings they might differ. But for our purpose, it's fine if we use low pass slash band limited. So hence it is possible that it is a low pass slash band limited signal. Then Nyquist criteria works fine. And the explanation we gave, Nyquist criteria works fine. Okay, replicas, let's just say what we did was replicas overlap, avoid overlap to determine the sampling rate, the optimum sampling rate, whatever it was. So this was pretty much the logic or the development. But in reality, let us say in reality, signals would be definitely time limited. This you can clearly see from all real life examples. If you are talking over phone, if let us say we are having this video call, so whatever we are doing is always time limited in nature. We cannot have something which just exists from minus infinity to infinity and we want to communicate that into someone. Okay. Now with this as the real case that signals would be definitely time limited, how do you really then sample them? Now if that is the case, then its spectrum cannot be band. This we have seen in our last lecture. But there is a possibility that this spectrum has, but with a smoothly varying time domain signal, quite possible that spectrum has very low power, high frequency component. Okay, that is quite a possibility. Okay, why? Because you may not find that signals vary too much in a small time frame. They may be, but in most of the settings, that signal will be somewhat smooth. It means that its characteristic in the frequency domain, if at all it is strictly, if it exists from minus infinity to infinity, we said that let us say the spectrum can be like, but this won't be a reality because the signal won't be existing from minus infinity to infinity in the time domain. So what will be the case? That maybe that you will have some sort of a low power, high frequency components or something. Or maybe that the signal is like this, and then it goes down to zero after some time. Not zero, but approximately zero. So it is not strictly band limited. Okay. It has a few components of high frequency and the power is less. So in such scenarios, how do you do sampling? So how do you do sampling in such cases? And this is what is the most important part of the sampling study. It means really use stuff. When you want to use it, then you have to use it this way, the way which I will be telling you. So what is the best strategy? So if at all we see this, the best strategy is choose a sufficiently higher, I think higher than Nyquist range, obviously. Now there is a question that if the signal is not band limited, how do you define this higher than Nyquist range? For the time being, you accept this, so choose a sufficiently high sampling rate. Okay. To avoid spectral overlap in the maximum sense. Okay. To avoid spectral overlap sufficiently. That will be put down to zero. Now let us, but there is one issue. Still, there we cannot say with this, it cannot be said that overlap will be zero. Okay. So then let us see how do you study this thing. So in order to tell that, or in order to see this, let us see one figure. Okay. So this is being given in the BP Lattice book, pages 260. You can clearly see. So let us assume that G of f is the spectrum of a time limited. Okay, this means that this is not turning out to be zero at this point. This is now taking value after this point. This is taking values which are very close to zero, but they are not strictly zero. Otherwise, it becomes a band limited, okay, which is not there because our signal in the time domain is time. So assume this is a sort of a spectrum of that time limited signal. Now you sample it at some rate fs, okay, or omega s. They are both related by 2 pi fs. Omega s is 2 pi fs. So if at all we do that, so you know that the signal, the spectrum which we obtain will be the shifted replicas of the signal. So this you can clearly see here. Okay. That this is the original signal, original spectrum, and this is the shifted spectrum. So the lines which are in light, which are lightly dark as compared to the other lines, they are the original spectrums. Okay. So what happens that at this frequency, this is nothing but fs by 2. At fs by 2, we have a sort of this sort of an overlap. Now, what it causes is this causes the spectrum to become negative. Even if we choose any higher f of s, this is f of s. So if we choose any possible value of f of s which is sufficiently high, we cannot avoid this. So it means that near to fs by 2, our spectrum changes. Now, this is a problem. If at all our spectrum changes, now once we try to recover our signal after sampling, we won't be getting the exact signal. So this is the problem which will be there even if we choose a sufficiently high sampling rate. This can be clearly seen from this figure. Now you can observe. Let me just take a. So this you can see. This is the original spectrum. Okay. This. Now, and this is the spectrum which comes after shifting this signal to fs. Now, since we know that this is not going to be zero after this, it means it is not strictly band limited. Okay, so this goes up to infinity with very low values. So definitely both the spectrums will collide at some point. Now you can observe this. Let me draw it for you that if at all there is anything, let us say if something is of this form or of any form, if I shift this zero to some frequency, let us say fs. Okay, so you will say that let us say this is your spectrum. So this frequency where both the curves will intersect is nothing but fs by that is half of this frequency. At half of this frequency, both the curves will definitely intersect. So this frequency has a special name that is called as the folding frequency. So we will write it down. Now, what happens because of this is that in this region, the spectrum distorts. Okay, there is a distortion. There is a distortion in this region. Okay. The impact. What will be the impact? Clearly, signal recovery won't give me the original signal back. Exactly, it will have some sort of issue in that. It will be a distorted copy of the original. So how do you handle this? So what is the way out? So we will study this, okay? So I will study, while studying, I will write few things down for the sake of completion, okay? So first of all, yeah, let me just again come back to this. So what was happening was that, let us say this was the folding frequency, or this is the frequency at which both the curves, the shifted replica and the original signal or the original spectrum collide. And in this region, the spectrum takes a different shape. Now, if I apply a low pass filter, that is called as a reconstruction filter. So we saw in the last class that the reconstruction formula, which comes through the standard derivation, in which took sinc function as the interpolating function. So that is nothing but passing the signal, the sampled signal through a low pass filter. So this is nothing but a low pass filter. Now, if I pass it through a low pass filter, suppose it is realizable, so you will get this spectrum, the darkened one, this one. So you can clearly see that in the high frequency, which is approaching fs by 2, the spectrum is now different. Okay. So let us say this is the spectrum which you get after applying a low pass filter or after reconstructing the signal. So let us say there was a GT whose spectrum was G of F. I sampled GT and I collected G of NTS. And after I collect G of NTS, I use a sinc function or I pass it through a low pass filter. And let us say the signal G cap T which I obtain has a spectrum which is of this form. Now clearly see these gray regions show that basically, if at all I need the exact time domain signal, then I need to have a spectrum like this. But the spectrum which I get is like this. This darkened line shows me the spectrum which I obtained. Okay. Now, what is really happening here? See, this is the original spectrum or the spectrum of the signal, and this is the folded or the shifted replica. Now, both of these things are adding. Okay. So this is what is called as the folded tail distorts the lower frequency. Now, what is this? This is like this tail is now folded back into because of this some sort of a symmetric spectrum. So you can say that this tail and this tail is somewhat similar. So around the folding frequency, this folds and this adds into the complement. Okay. So this is called as the folded tail distorts lower frequency. Okay. and lost tail results in loss of higher frequency. So let us say around fs, you call fs by 2. This is the lower frequency and this is the higher frequency. So applying the low pass filter, this high frequency is completely lost. This is lost. And these lower frequencies, which are just less than omega s by 2, they are distorted. So if at all we work with the strategy, so let me just write it down, that referring to the figure, referring to figure, okay, what is this figure 6.8, page 260, figure 6.8, page 260, that is book. We observe that even after choosing a sufficiently higher fs, and we land up with dual loss. Now what is this dual loss? Okay, let us see what is the dual loss. That, let us say if I study one copy, and this is what is the case. Suppose this is my f of s, this is my 0, and this is nothing but f of s by 2. And if I am applying a low pass filter, okay, at this frequency, so this tail is lost. So this is lost, which is bad, because ultimately if we are going to construct a time domain signal back, these components are required to get an exact copy. But one more loss happens. What about this region? Now, because this waveform or this adds to this, instead of getting this, you get something like this. This shape is like this. So you can clearly see in the figure here. I think it's properly drawn here that this folded, this folded tail which comes back because of this replica adds to the lower frequencies, or the frequencies which are lower than omega s by 2, and the spectrum takes a different shape. So using higher sampling rate, then low pass filter leads to dual loss. Okay. So how to avoid that? Now, how to work? Now, what to do? So this is the question now. What to do? So the strategy is, why not low pass filter the original signal before sampling? Okay. Why not do that? Now, what is the impact if at all we do it? Let us see. Yeah, let us see. So this low pass filter is referred to as an anti-aliasing filter. Now, why? Because here, if we are not low pass filtering, we are simply sampling at a higher rate. Still, this collision of spectrum is taking place. So let us say, so that collision we are calling it aliasing. I have not yet defined what aliasing is. I will define it. Once our discussion is complete, then I will write few things down on this OneNote document, so that once you go back and read the notes, things are quite complete. So let us say we put an anti-aliasing filter before sampling. Okay, so first G of t, that is the original signal that passes through an anti-aliasing filter, and then we sample. Okay, and then we obtain the sampled waveform, or you can say the sample value. So what is now the impact? That because of us passing it through a low pass filter, the spectrum, if it was like this, it means that this was having some non-zero values for higher frequencies. After we pass it, let us say, through this sort of a low pass filter, so we will get a signal of the form like this. So we have strictly basically band limited. Now you can say that we have induced a distortion at the starting point itself, but there is no choice because what we do in theory somewhat sometimes doesn't translate into reality exactly. So we need to make few exceptions or we need to make few ways to use theory in reality. So this is what we're doing. That first we need to sample it through an anti-aliasing or sorry, we need to pass it through an anti-aliasing filter and then we need to sample. So this is now what will happen. Okay. So let us say if we see the spectrum of GAAT, so this high frequency, because we have already filtered it, so these frequency components are not there now. But the benefit now is that if the high frequency components are lost, the low frequency components are intact. So this we can say that here there was a dual loss. These high frequency components were chopped off or they were left out because of the low pass filtering, but the lower frequency components just below fs by 2 were also getting discounted. But now we have somewhat avoided one of our losses. There were two losses, so we have somewhat avoided one of our loss by somewhat retaining the frequency components which are below omega s by 2 or fs by 2. So this was the concept I wanted to highlight before we I can move ahead with the PAM and other sort of waveforms we want to discuss. So I think this was the concept which I wanted to say. Now for completion, I will write three things down. That is the definition, let us say, of the folding frequency and the definition of aliasing. Why do you call it alias? Because I think if you remember that when we read newspapers, so we will find that some name like Rahul, alias Salim, or whatever you call it. So this alias means that someone who is known by another name as well. So this is our familiarity with the word alias. Now, why does this comes here? The aliasing in sampling. So the question, look, this is really a question. So as engineers, we need to ask that, okay, if somebody has coined this term, then what is the reason for that? So I will write it down. So then you will realize that, oh, that is why we call it aliasing. So for a few minutes, bear with me. I will be writing few things down. You can just read. So first of all, let me define the folding frequency. Anyways, towards the end of the lecture, you will get the breakup file. So there I will mention the source. So you can go back and read from the textbook directly, which I would say that you should prefer reading from the textbook. So this is fs by 2. This is the folding frequency fs by 2, which is nothing but 1 upon twice of ts hertz. Okay. So at this, what is happening is the spectrum may be viewed as if the lost tail is folding back into itself. At the folding frequency. Okay. Now this is very logical, and you can see. Let me just go to that. Yeah, you can see that this. So this, let us say, this is the point, and I place a mirror over it. Okay, you place, suppose a mirror you place. Now in the mirror, if you see this, this part of the spectrum in the mirror, you will find that this will be taking like this sort of. So that's why this is called that what I have written in that spectrum may be viewed as if the lost tail. So this tail was lost because of the low pass filtering is folding back into itself at the folding frequency. So this fs by 2 comes with the, now this fs by 2 is a very means general thing. It is not for this spectrum it is valid. You can just visualize that. Let us say if you have a signal, but yes, the spectrum should be that the low pass that component at the high frequency are low. मतलब इसी तरीके का स्पेक्ट्रम होना चाहिए. उसी पे आप जब विजुलाइज करेंगे तो आपको ये clearly you will be understanding it. So a spectrum of the sort in which high frequency components are low power. Okay, so low frequency components take most of the power. That's why we are studying this sort of signal. Okay, because in reality, for generally most of the signals are like this. Okay, that's why we can sample them easily. Otherwise, sampling, if you sample it, that's fine. But when you reconstruct it, they won't give you the exact signal back. But yes, there is an exception in image processing. Why? Because it depends on our perception. Sometimes the human ears, they cannot they cannot basically observe the phase changes in the speech, the reconstructed speech and everything. It's fine for them if they can understand. Similarly, with respect to viewing also. Okay, so their sampling sometimes puts distortion as well, and those distortions doesn't affect the quality. Okay, so this is called as, so at this point, if you play something and you view this remaining tail, you will find that this has now folded back. And after folding back, this is distorting the low frequency component. So this is nothing but the folding frequency. Okay. So now let us define the alias after defining the folding frequency. So components of frequency, let me write it down. Components of frequency fs by 2 plus f of z. Suppose this f of z is some arbitrary frequency value in hertz, shows up or impersonates. This is important, or impersonates a component of lower frequency. Okay, lower frequency, that is fs by 2 minus f of. Okay, let me just write a small z here because it is. Okay, in the reconstructed signal. This you can see from the figure I shown, reconstructed signal. Why? Let us see this. Now again, we will go back to our figure. Now if suppose I take this as the value and this as f of z, suppose. So I can say that this is the value which is fs by 2 plus f of z. This is the value at. Now if you correspondingly observe this, okay. So this is nothing but, this is also f of z. So fs by 2 minus f of z. So at this value, at this fs by 2 minus f of z, the original spectrum had this value. But now this value gets distorted by the value here. Okay. Or I can say that this component takes value inside or impersonates. So when we say that Salim impersonates Rahul, it means that Rahul and Salim are now same. It's Rahul alias Salim. Okay. Let me write it down. Thus, components of frequency. Thus, components of frequency above fs by 2, reappear as components of frequency below fs by 2. Okay, this is known as, so either you call it as spectral folding or alias. Okay, this is known as spectral folding or alias. Okay. So this logic and this Rahul alias Salim will now let you understand that there is a reason behind calling this phenomena as aliasing. That is the basically the, what do you call, the intersection of the two replicas, or sorry, you can say the original one and the replica one. Basically, aliasing will be defined for all subsequent. See, there will be several spectrums towards the right and towards the left. This you can see clearly from this book. Okay. So while drawing, the drawings are somewhat now not very good. So that's why I've just drawn two possible spectrums, but generally the shape would be like this. So that's why I'm projecting this figure from the book directly instead of drawing it, so that you have a clear understanding of what we are doing or what we are studying here. Not doing, but studying. Okay, so now this is aliasing, the phenomena of aliasing, or you can call as the spectral folding, because you can say that here we observe that this spectra folds back into the original spectra. And these components which we were thinking are lost, now they are not lost. They have now folded back into the spectrum and they have distorted the spectrum. It means you can see that they have two copies. One is here and one is here. And that's why this phenomena gets its name as aliasing. Okay. So now, I think let me write this anti-aliasing thing down so that if you go back and only read the notes, you know. So the anti-aliasing filter, eliminates the components above fs by 2, eliminates the components above fs by 2, folding frequency, from GT before sampling. So now with whatever I have explained, if you will go back and read the textbook, and this one very important, this is called as a hack which you need to do for real-time saving. The hack means that you need to just pass it through the anti-aliasing filter before sampling. You will understand the reason behind it. And this is a very, very popular question. Okay, why I am now investing more time in module 1, because uh, this forms the core of digital communication and the modern communication, we should say. If we are, as engineers, if we are not clear with what do we really do in sampling, although this is what called as the A to D converter. Okay, so A to D converter is have been studied very deeply in VLSI as well as in signal processing, and they have several things to do. Okay, means you need to study them. There were several issues in practical sampling which were handled by the researchers. But for us, let us say we are starters in the field. We will be having a BTech degree and we'll be working somewhere. For us to be able to work somewhere, we only need to know this. So that's fine with us that we know this. But we need to know this problem. Okay. कहने का मीनिंग ये है कि जानने के लिए बहुत कुछ है, पर इस स्टेज पे आपने इतना जान लिया वो भी अच्छा है, वो ही बहुत है, क्योंकि आगे आपको और डीपली स्टडी करना पड़ेगा. If at all you want to specialize in A to D converters, the design of A to D converters, if you go to companies making A to D converters, okay, and there is a big unit which makes this. Okay. Now one issue, I think we have not yet studied one thing that is very important: realization of ideal filter. Okay, realization of ideal filters. I think we have not said anything about it, which is also one of the last things to study in sampling. Okay. After this, we will immediately go to the pan waveform. So this is what we will be studying now. Let me see if I have written everything here or not. We will check. Yeah, except for this, I've just written everything. Rest, if at all something is missed, so when I will give you the reference in the lecture breakup file, you can go back and read it. If there is any issue, doubt, or anything to say right now, you can just unmute and tell me. Okay, so we have 142 people in the class today. So if at all you have anything to say, you can just tell. If you cannot understand something, if you cannot understand anything, then we can still have a separate session where I can explain it to you as per your convenience. That is the way you can understand well. So realization of ideal filters, what do we mean by? See, we have relied up to now. So we have relied up to now on filters which can exactly bring out a part of spectrum process. Okay. For example, let us see this figure back. So this is what we have drawn. This dotted line shows you the ideal field. So now let us ask ourselves, is it really realizable? It means if in real time, when I say that my input signal is not time limited, okay, so it cannot be band limited. But if at all we say that exists a filter which is band limited. Now, what is this? This is band limited filter. It can theoretically it is bringing a spectrum with from minus omega s by 2 to omega s by 2 exactly. Okay. So if I talk of its time domain response, then as per my theory of a signal not being time limited and band limited simultaneously, the time domain response of this filter will be extending from minus infinity to plus. For example, let us talk of the sinc function. Suppose if we say that if at all this is an ideal filter, okay, this is f and this is mod of g of f. This is an ideal filter. So what is its time domain response? The time domain response is the sinc function. Now the problem with sinc function is that it extends from minus infinity to plus infinity. So how do you realize it? One problem is this, that it exists from minus infinity to plus infinity. Now the second big problem with this, if this is your, if instead of g of f, if I use h of f as the terminology, because we are familiar with h of t being the impulse response. So let us go back to the terminology from signals and systems. So this is your h of f. If this is your h of t versus t, okay. So h of t is non-causal. Non. Why? Because h of t is the impulse response. Okay. Now the problem is that impulse response says that if I apply an impulse, this is suppose you can say time, sorry, t time, this is 0 and this is your delta of t. But the problem is that this filter is having an output before even the impulse is applied. Why? Because for the whole negative axis, it is giving you some sort of an output. So even before I apply an impulse, this filter is giving me an output, which is undesirable. See, unless I apply something, I should not get something in real systems. Okay. So because of it being non-causal, it is unrealizable. Okay, and in spectrum line, oh, sorry, it's time domain response line from minus infinity to plus infinity are having a very large time domain response. This is unrealizable. Now again we are why we are stuck, because somehow we handled our non-band limited feature through anti-aliasing filters. Okay, somewhat we handled our the issue which we have just studied through the design of this anti-aliasing filter. But now we rely heavily on this ideal low pass filter. So how do we do now? Because again we get a problem. Okay. So what is the issue? Let us do one. First of all, let us try, because we know that the sync function has a very sharp die down. Die down means if at all this is 1, if at all this is 1, then these amplitudes are somewhat reduced, very much reduced as compared to 1, and these amplitudes go on decreasing. So one possible way is let us now shift the sync function towards the right, okay, to make it a causal sort of a response. Okay? It won't be causal, but let us say that we shift it to some tau value. Okay, this is some tau value. Okay, so shift the sync to right. Shift the time domain response towards right. Okay. So this has taken my main response or my main thing towards the right, but still this thing remains. Okay. So what to do? You cut it off. Okay. It means that you just apply some rect function, that is h of t into rect of, or u of t, you can say. Better is to use the u of t function instead of rect function. U of t would be better. Okay. So use h of t into u of t. Now this will give you what? It will give you that. So this has now avoided both, at least this non-causality issue of the ideal filter. Now this filter is causal at least because the response starts from zero. Although this response extends to infinity, but still you can see that this will be dying down very fast. But what is the impact? See, what is the impact? Now the time domain response is because h of t into u of t. If I take the Fourier transform, this is h of f convolution with the Fourier transform u of f. So it doesn't now remain to be a response of this form. Okay, now the filter doesn't remain here. So it cannot give me now, it won't be having this shape. It won't be having this shape. Okay, now see. So because of whatever we studied in signals and systems, if at all I or you are the engineers who need to make this sampling system work, we are studying that whatever hack we use, what impact it has. So let us say if we use this hack of shifting and multiplying with u of t. Sorry, I think h of t I have written, but it will now be having h of tau t minus tau or something. Okay, so just we change it, and this h of f will also have some exponential factor of some function. Okay. So we use this hack that we shifted it towards the right and we multiplied it with step function, but then it has altered our frequency response. And now, since this has somewhat become a time limited thing because of its convolution with u of f, this won't be having a band limited nature. So now it won't be having this shape and it won't be band limited. So now how do you work with the sampling system? Again, it means that now we need to again do some sort of an engineering. But here there is one more impact or one more thing to notice, that there is a big area of filter design. Okay, which says that, so now we work with approximate band limited filters. Okay, it means those filters approximate band limited filters. What is the logic behind saying approximate band limited? If I at all, instead of having this sort of a characteristic, I'm not drawing the minus frequency, this will be having this. Now my filter might have a response of this nature. Okay, it means that it has a pass band which may not be strictly terminating at some frequency omega p. You can say that this is a 3 dB bandwidth. Let us say that is some omega p is the 3 dB bandwidth, but it still dies down sharply after some omega p plus delta. Okay? So you cannot say that the spectrum which we have drawn here will be having its sharp cuts at these. But yes, we can definitely control these side lobes. Okay? These are called as side lobes. So as compared to the main lobe height, let us say this is your h and this is your h prime, we can say that h upon h prime should be greater than, much more greater than 1. We can design such filters, those who are causal as well as have a limited time domain response, and they have some sort of a band limited nature. Some sort means that of this form. So digital filter design, analog filter design, that is a big area. So we need to understand that even this thing, that ideal filter doesn't exist, and we do these sort of designs to approximate such filters. Okay. The reason for this, I have already told you that the filter is non-causal and it is unrealizable. This is not t. Say, if you have a h of t, some block generates h of t, this h of t. Without even applying an input, you're getting an output. So such a system is unstable. Should be, means in reality, this can create problems. So you want a system in which once you apply an input, it should give you an output. So this causal and non-causal theory of studied in signals and systems. So we can assume that if at all there is some confusion with regard to this, you can go back and study. Okay. So this non-causal nature gives you a problem, gives you a trouble. Okay. And one more thing, that is a Paley-Linear criteria. This is for the interested reader. So I am writing it down before closing this at least topic. For the interested reader, this may not form a part of our course. This is given in both the textbooks. Okay, this is a Paley-Linear theorem you can study, which tells us that any sort of a spectrum which dies down to zero in frequency is not reliable. Okay, this is a very, very important and strong statement. You can just study. This is given in both the textbooks. I think given in Latti's book, given in Latti's as well as I think other textbooks as well, Latti and other also. And this tells let us let us respond, which strictly goes to zero in frequency. Strictly goes to zero in frequency is not reliable. Okay, is not reliable. So this is for the interested reader only. If at all you are somewhat confused that why not we can have sharp filters. It means filters. Even let us say you can say that why can't we have why can't we have filters of the nature where this dies down to zero after some time? Means you can ask that why is it the case that after some omega capital C this strictly goes to zero? Why not? So this answer is obtained by this. So if at all you are an interested reader that you are deeply studying sampling process, then you can go back and read this. You will find a reference there for the original work of DAIICT. So in order to see original works and the way people studied, I have just uploaded one paper. I think in the last class, in the last lecture, I uploaded one paper where you can see that how do we study the sampling of band pass signal. So now we are done with this sampling, and now you can, those who have not yet started reading, they should go back and start reading. At least full sampling they can read. I have given references. So now today we'll start with uh, pulse amplitude modulation. Okay. Ultimately, for this module, we need to study pulse code modulation PCM and DPCM. That is the last thing for module 1. For module 2, I think things would be easier because you have undergone a lot from module 2 in your CT111 course. So we will be studying those things which you may not have undergone there, or the things which you have undergone there in a deeper sense. Okay. So pulse amplitude modulation we will be studying. So here we will be using some signal processing or signal systems again. So you will realize that studying that course was not worthless. It's quite useful. Otherwise, let us say as an engineer, whatever you plan, okay. So as an engineer, while designing systems, whatever you plan, how will you study those? Okay, I know that we are not the people who will develop theory. That I completely accept because engineers, the purpose is that if somebody has developed some theory, how do you really apply it in real? That is what is expected out of an engineer. So I know that we won't be developing theory, but if at all we create some hack, this is what the term I'm using, that if we create some sort of a hack or some sort of a possibility, how do we study it? What is the impact on the system? So let us start this. So sampling theorem provides a way. So sampling theorem a way provides a way to reproduce an analog waveform, by using sample values of waveform and sine of x by x orthogonal functions as interpolating functions. Okay, this orthogonal I have just used loosely because we have studied the orthogonality of these functions. Okay, we have undergone this when we were studying the cardinal series. We derived. Okay. Now, what does PAM do? So PAM provides another waveform. PAM provides another waveform that looks like pulses but contains information present in analog waveform. Okay. Now, there is a question that why does this pulse amplitude modulation hold some value, or why are we studying a pulse and then we amplitude modulate it? So let us say there is some pulse, you can take any sort of a shape of this pulse. Suppose you take this as a shape, or you take this as a pulse shape, okay, or you take this as a pulse shape. So suppose these are some examples of pulses, and we are amplitude modulating. So we take pulses and amplitude modulate them. Okay. So the question is why? Okay. So the thing is why? So let us say if you talk of a CD player, for example, let us say if you talk of a CD player. Now CD players now do not exist that much. It means they are not in use. Earlier they used to be. So on CD players you have digitized the song or the video and you have stored. Now the CD player, the purpose is to take those discrete samples and generate them. Now if it tries to use the standard interpolating function, that is the sin x by x function. So interpolating through sin x by x seems to be a difficult task. First of all, sin x by x is or sin function is a waveform which, or a pulse. It should not be called a pulse, but it should be called as a function which exists from minus infinity to plus infinity. Now creating several shifted copies of that, multiplying it with the waveform samples and then generating the whole waveform somewhat imposes a lot of constraints on the circuitry. So what you do is you say that if at all my samples are coming like this, it means that let us say my samples are taking these values, a function of time, let us say on the time axis, these are discrete samples which I have stored. So why not if I have this much of gap in between, let us take some sort of a small pulse or something and capture this information, the amplitudes, in some way in this pulse, okay, and generate a continuous time signal, okay, to generate a continuous time signal. Now, why are we interested in pulses only? Why? Because they can be in a continuous time. Why are we interested in pulses? They can be easily generated through circuitry. Okay, pulses of different form. It means that I am just drawing an arrow in front of this red type of pulse. Doesn't mean that only this pulse. Any sort of pulses like this and this, they can be easily generated through a cheap hardware circuitry. Okay, can be easily generated and be easily generated through cheap. Okay, I mean write a circuit as well. For example, you can have a capacitor whom you can discharge instantly to generate a sort of pulse. For example, let us say if you have this sort of a switch and you have a capacitor here, suppose, okay, and you have another switch here and you have some source, okay, maybe you can call it analog source or a DC source, whatever you have a source here, okay. You close that switch for some time, the capacitor charges, okay, and let us say this is my output voltage VO. So once it charges, so it will, let us say the waveform like this, it charges, and then after some time, let us say this the charge, after some time you close this. So once you close this, the charge V naught is the level which it's maintaining. As soon as you discharge, it goes. So this pulse is easily generated through this circuit. So these circuits you can find in several books. Right now, our focus is not on studying the hardware to generate these waveforms. These will be covered in labs. We have basically deliberately kept three hardware labs for all of you, even though we are in the pandemic situation. But Professor Godgaonkar will be recording those labs and will be giving it to you so that you get familiar with the circuitry as well. that whatever we are studying, how do you do it on hardware. After that, we would be having all MATLAB based labs. Okay, so we had two choices. Either we could have just worked with the hardware lab or with the software lab, but we took a mixture of both so that the learning is more. Okay. So with this as a background, we will be studying, let us say we can generate pulses and we have discrete samples, and between two samples we can generate a pulse. So how do you capture the information of these discrete samples through these pulses? So first category is amplitude modulation. Okay, it means that let us change this level. Suppose this is some 5 volts and this is some 3 thing. So we can have some sort of a waveform like this. This takes the value 5 and then this takes the value 3. Okay, fine. So this amplitude captures the values of the discrete sample. So this goes on. Okay. So we have two categories of PAMs. I think I've written conversion now. So what is the definition of PAM? So conversion of the analog signal to a pulse type signal. In which the amplitude sorry, in which the amplitude of the pulse denotes the analog information. So just written the definition for completeness, denotes the analog information. Okay. So we have two classes of one is the natural sampling. This is also called as gating. Okay. And another one is instantaneous sampling. So we will study both. And then we will immediately shift to PCM. Okay, instantaneous sampling. This is called, sorry, instantaneous sampling to produce. The name is instantaneous sampling to produce. Flat top pulse. Okay. So before I go towards the study of natural sampling or gating, I would say that if you have anything to ask, even if you have anything to comment on, you can just go ahead and mute yourself and say for gating. So we'll be studying this. Why we call it gating, we will see. Okay. So if you have anything to say, you can unmute and say, or you can to ask something, you will discuss something. Any doubts? Okay. Okay, so there is no doubt and there is nothing to say. Let us move ahead. So there is an analog waveform. So we start with an analog waveform. This is important because after studying sampling, we know that the concept of signal being band limited is very, this is called as a very important or the heart of sampling. Okay, band limited in some nature. You can say that the high frequency components are of very low power. Okay, so the analog waveform. So right now we are ignoring this issue of time limited and band limited because we know if at all that is the case, and that is the case in reality, how do we handle that? We know that. So for the theoretical analysis, assume that analog waveform is band limited to B hertz, okay? And we call it as suppose WT, that is analog waveform. Now the naturally sampled or PAM signal is what? Naturally sampled or PAM signal. PAM signal is given by multiplication of WT with a waveform S of T, where S of T is what? Let me write it down. So S of T is summation k equal to minus infinity to infinity, the red function t minus kts divided by tau. Okay. Now, one thing I think this natural sampling or gating I've discussed earlier as well. See, what are we saying is that if at all you have a waveform and you try to sample this waveform with some sort of a circuit, circuits will do that, no? Whatever we are studying is theory, but anything in hardware will be done by some circuits. Okay, so we put it through some circuit. So what that circuit does is that it takes the waveform, suppose, and it operates a switch. Okay, now this switch closes and opens. Now this closing and opening operation might take some time. It takes some time. That is quite possible. Time. Okay, so what happens that this waveform, let us say this is W of t, and this is your t, this is passing through this circuit, and the output which you get is, let us say if I am at this point, and my circuit, this switch closes, and the output at this is again Wt, but for some time. Okay, up to the time this switch again opens up. So we will get this point. Then again this switch closes at this point, and we will get this. Okay. Then this switch closes, and then we get this. So this, the tops of these pulses are the values of these functions. Okay, it takes exactly what the function is there. So these tops of the pulses are nothing but the values of the original function. So if this is what is being done, because this is what the way you will sample something. So that's why the name comes natural sampling or gating. It means there is some gate which closes for some time, it opens back, then closes and opens. So this is equivalent to saying that if we create a time domain clock, okay, if we create a clock, I think you must have studied this clock in embedded systems, that there is a clock. This is a clock which operates this switch, okay. A clock operates the switch. So ultimately this operation, the output can be written as product of this clock with the time domain signal. So I can write, or for the study purpose, I can write. For study purpose, it means I need to study what is happening. For study purpose, I can write the obtained waveform as obtained waveform as product of original signal product of original signal and the clock. Okay, that is why this term comes omega t into s of t. S of t is this. Let us first see what is pi of t and what is this, so that those who are not very clear about this. So what is pi of t? Pi of t is a time domain vector pulse, and this takes value from -1 by 2 to 1 by 2. The value is 1, this is t, and this is your t. Now I do two operations. One is that first of all I will draw pi of t by tau. This all you have studied earlier, so I'm just, instead of asking you, I'm just writing it down so that you don't waste time in this since you have studied. So this will shift to what? This becomes minus tau by 2, this becomes tau by 2, the amplitude remains 1, c. Now I shift it by, suppose, k of ts. Okay, this is what is being done. So if I shift this, it means now you change t by t minus k by ts, and this whole is now divided by tau. Remember that this tau doesn't remain in division to t, it is being divided by a full. This is what? This will shift this waveform to k of ts. Okay, and this will be k of ts plus tau by 2, and this will be k of ts minus tau by 2. Okay, this one. The amplitude still remains 2. Now if I add it, now summation k from minus infinity to plus infinity, this whole term. Okay. So when you sum it, so you will get. So this is exactly your clock signal, which we have just studied. So this will be 0, this will be PS, this will be 2PS, this this will be tau, the gap is tau. Okay. This is going from okay. Let me draw one waveform for minus also, otherwise those who won't be studying it with that much of tension, they might feel that we only have this in the positive side. So this is the signal or the clock signal, you can write it like this. See, I could have just moved ahead with saying that this clock signal can be written like this, but because I know that even after going through the course, sometimes we don't know how really this comes. So I just told you that how this is derived. One important thing to say that pulse rate means the time after which another pulse comes, or pulse rate f of s is equal to 1 upon t of s, which is strictly greater than equal to 2b. This is from the sampling theorem, okay? From sampling theorem. And obviously, one thing to say that tau by Ts will be less than 1. Okay, this is important. Otherwise, these pulses, they will basically interfere with each other. Okay, so this is also called as switching waveform, switching waveform with duty cycle, duty cycle. It will d equal to tau by 2s. Now, here in our case, it has to be less than 1. Why? Because if at all this is not less than 1, once you shift it by Ts, both the pulses will interfere with each other. So this tau must be less than Ts. Okay. So I think I have drawn this sample signal. So now with our definitions complete, let me just draw that this is Q of tau. So the time it takes for the switch to remain closed or it remains closed for tau seconds. Okay. Closing and opening operation takes the total tau. So in that time, you will get the shape of this. The height of this is nothing but the shape of the original signal. So that is the difference between natural sampling and instantaneous sampling. In instantaneous sampling, you will have flat top pulses. But in natural sampling, you are not having flat top pulses. You are having exact shape of the signal. Now, when we will study it through the Fourier transform and everything, you will observe that quite a difference is there. Okay, quite a difference means that the recovery will have a different setup in each of the points. Okay, because natural sampling, the spectrum doesn't get distorted that much, but in instantaneous sampling, the spectrum gets distorted. So we need to use an equalizer. Equalizer means the effect which this process has on the spectrum needs to be nullified at the receiver. That is called an equalizer. Matlab, somebody destroyed and then somebody builds. So whosoever builds is called an equalizer. It means whatever bad has been done is now equalized. So we need to start with the spectrum of WST. Spectrum of WST. Okay. So the step to do it is quite obvious. If I take the Fourier transform of WT into S of T, I think I have not yet defined WST. Yes, yeah, this is WST. Mutually sample kind of signal. Let me just draw. Okay, so this is W ST. So obviously, if you need to define the spectrum, you take the Fourier transform of WST and you will get this the Fourier transform of the product. Now this is nothing but using the property this WF convolution with the Fourier transform of S of t. Now you know that S of t is a periodic series. Okay, this we have answered. This is a periodic series. So for this periodic signal, I think I have already told this, but just for the sake of repetition, let me write. So this can be written as a Fourier series. So we can write S of t as a Fourier series, this way that S of t is nothing but summation P of n e raised to power j n omega n t, where n lies from minus infinity to plus infinity, and omega s is nothing but 2 pi by ts, and where c of n is where c of n. So I have already, I think, noted it down that what is the Fourier series coefficient for such a thing is n pi t upon n pi t. Okay. Remember that d is nothing but tau by t. This is the duty cycle. Okay. So since ST is periodic, since S of t is periodic, its its spectrum can be written as S of f is equal to summation n is equal to minus infinity to infinity P of n delta of f minus n. Okay. So one last thing I need to write before we close for the day. So WSF is nothing but summation. I think you can clearly follow the derivation from this. You need to convolve both of them. Okay? You need to convolve S of f with W of f. So once we do that, so this can be written C of n W of f convolution with delta of f minus f. So this you will obtain it. Summation C of n W of f minus n of. Okay. So we will, I think this is a very small derivation which you can easily understand. So we will study this in the Friday's class, and we will be done with what is happening to the spectrum of naturally sampled band, and then we will study the instantaneous sampling. Then we will shift to PCB. Okay. So we are done for today. If you have any doubt or if you have any comment, you can unmute and say, I am here for another 5 minutes. Okay. So this week there was no lab, but from next week we will be having 3 labs which are hardware based, and subsequently all the labs will be MATLAB based. So in the meantime, just go through the theory because the labs are based on pulse position modulation and pulse width modulation, the hardware circuitry. Okay. So you have kits, and on those kits you can uh, study this physical phenomenon. Okay, then we'll meet on Friday.